In this video series, we have been looking at inference for multiple independent samples when we have a quantitative response variable. Now it is time to move beyond two samples. Let's look at a Fisher-Pitman type randomization test for K samples. One of the most commonly used designs in behavioral and social research involves the comparison of scores in K conditions where K is greater than 2. The only package required to follow along with this presentation using R is the coin package. Here's the setup. We have random samples from K populations where K is greater than or equal to 2. We have either K independent existing populations, and we draw a sample from each, and we want to compare these, or we could have a single sample from one existing population, and we randomize participants into conditions, each condition representing an additional potential population. We have independent observations within each sample and a quantitative response measure. Here's an example. A study of the effectiveness of metaphors compared 3 conditions: a control condition, an advanced metaphor condition, and an extended metaphor condition. Participants in the control condition received a difficult textual passage. For the advanced metaphor condition, the same passage was preceded by a familiar metaphor. In the extended metaphor condition, the metaphors were embedded within the passage. All participants then completed a comprehension test about the passage. The null hypothesis in this case is that the median of the first population equals the median of the second equals the median of the third. If we have more than 3 conditions, we can extend this null hypothesis to represent those conditions. We can include that this equals the median of the 4th population, equals the median of the 5th population, and so on. The alternative hypothesis is that at least 2 of the medians are different from one another. That is, the median sub k not equal to the median sub k prime when k not equal to k prime. A condition for valid inference about location, meaning a shift in medians, is that the distributions must have the same shape. If we do have the same shape, and we also have symmetry with our population distributions, the null hypothesis can be about the mean instead of the median, or in addition to the median, because the means and the medians are going to be the same in these populations. The null hypothesis in our example would be that the mean of the control condition equals the mean for the advanced metaphor condition equals the mean for the extended metaphor condition on these comprehension tests. The alternative hypothesis is that some of these means are different. But what if we don't have shape identity? In that case, the null hypothesis is that if we were to select a score at random from each of the 3 populations, the probability of a score being greater from one population than from the other 2 is the same for all 3 populations. The alternative is that there are some differences, that higher scores are more likely to come from one of the populations. In a nutshell, the alternative hypothesis is about whether higher scores tend to come from one population, and the null hypothesis states that the population we draw from tells us nothing about the probability of obtaining a higher score. Here are the scores obtained in the study. These are the comprehension test scores for each of the 12 participants, 4 in each condition. Here are the control scores, 9, 10, 6, 11. Here's the scores in the advanced metaphor condition, 13, 5, 7, and 8. And here are the scores in the extended metaphor condition, 15, 12, 17, and 14. The sample sizes are 4, 4, and 4 for a total sample size of 12. The number of ways that these 12 scores could be arranged into groups of 4, 4, and 4 is 12 factorial divided by 4 factorial times 4 factorial times 4 factorial. In general, it is the total sample size factorial divided by the product of the individual sample sizes, each factorial. In this example, there are 34,650 different combinations of ways that we could assign these scores to each of the conditions. You can see that the number of combinations grows very large, very fast. This is quite a small study, and yet we still have almost 35,000 different possible combinations. Where do these scores come from if the null hypothesis is true? Well, the null hypothesis being true means that the metaphor conditions have no effect on participants, so the score that a participant gets within a particular condition is only there because of random assignment. They could just as easily have ended up in one of the other conditions. Therefore, each combination is equally likely because it is all based upon random chance, nothing to do with a treatment effect. If there is a treatment effect, then in fact we would expect higher scores to come from one of the metaphor conditions, and each combination would not be equally likely. So it is only under the null hypothesis that each combination is equally likely. Let F be the usual F statistic from the analysis of variance, where F is the mean square between conditions divided by the mean square within conditions. We will calculate F for all of our combinations. In this case, we have almost 35,000 of them to calculate. We will sort the values of F from smallest to largest, calculate the cumulative probability, and then look in the upper tail of that distribution to construct a rejection region such that the probability that F is greater than or equal to the critical value is less than or equal to alpha. Let's calculate the F that we actually obtain with our data. Here I'm setting up the condition as a factor, the categorical variable. I'm looking at a combination of all the scores, and then I'm looking at an analysis of variance using score as a function of condition. That is, I'm doing the usual one-way analysis of means in order to obtain my F statistic of 7.7129. What about that p-value? That is not from the Fisher type randomization test, but it is the asymptotic approximation for the Fisher-Pitman type test. That is, with large enough samples, we will gradually approach the results that we would get from a standard one-way analysis of variance. There's an R function that can help us do the actual test. The number of permutations becomes very large very quickly, so this function does not do an exact test. Nonetheless, we can calculate the p-statistic in the coin package using the Monte Carlo method. That is indicated here when I indicate it as an argument that the distribution equals approximate. The default is to do this with 10,000 Monte Carlo replications. So here we end up with our Fisher-Pitman permutation test p statistic. This p statistic, again, is not exact. It is an approximation to an exact. That sounds a bit like an oxymoron, but it's the best way I can describe it. Whereas the default is 10,000 iterations, we could do it with more iterations if we choose, and this is how we do it. The distribution here is still approximate, but now we're mentioning that we want to resample 100,000 times. When I do this, I ended up with a p-value of 0.022. If you compare that to my asymptotic p-value, they're actually quite close to one another. That may be a little bit surprising because we had a sample of size 12. But again, if these scores are coming from a normal distribution, then it doesn't matter what sample size you have. You don't need an asymptotic approximation in order to do a valid analysis of variance. You can, in fact, skip the permutation test and do a valid analysis of variance. So it may be that these scores come from normal or almost normally distributed populations, something not surprising since we're dealing with comprehension test scores. So here I have a p-value of 0.022, very close as my approximation to the exact value for the Fisher-Pitman permutation test to what we get when we use an asymptotic approximation. We can therefore reject the null hypothesis of median equality because that p-statistic is small. And that assumes, of course, that we have equal distribution shapes. If we do not, we can still reject the null hypothesis, but now we're rejecting the null hypothesis that the probability of drawing higher scores is the same for all the distributions.